Supercomputing is the driving force of discovery in every field, from scientific to industrial, allowing researchers to understand the behavior of the smallest particles and visit the furthest expanses of the universe to unlock the meaning of life. And with digital twins, it's giving industries superpowers to time travel, letting them explore an infinite number of futures. And decipher the past through different lenses. And with million X higher performance, powered by accelerated computing, data center scalability, and AI, supercomputing will unlock new opportunities for us all.
Computing is the instrument of scientific discovery, the engine of industrial automation, and the factory of AI. Computing is the bedrock of modern civilization, and it is going through full-scale reinvention. For 2 decades, from the mid-'80s to the mid-2000s, CPU performance scaled with transistors, an order of magnitude every 5 years, increasing 10,000 times over 20 years. But CPU performance scaling has plateaued. Incremental performance comes with disproportional increase in cost and power. Meanwhile, demand for computing continues to grow exponentially across science and industry, driven by a broad range of applications, from digital biology and climate science to AI, robotics, warehouse logistics, and consumer internet services. Without a new approach, computing cost, and even more urgently, computing power, will grow exponentially in the coming years. Data center electricity has already reached nearly 2% of global electricity use. Exponentially growing demand is coming up against moratoriums on the energy consumption of data centers and corporate commitments to achieve net zero. The industry has awakened to the need to advance computing in a post-Moore's Law world. A 100x growth in computing within the next decade is unsustainable without a new computing approach. It is now broadly accepted that accelerated computing is that approach, but it takes work. Accelerated computing requires full-stack optimization, where software and hardware are co-designed. We optimize the entire stack, including the chip, compute node, networking, storage, infrastructure software, acceleration libraries, and the application. And this is done one application domain at a time. The work done for molecular dynamics differs from that of fluid dynamics, seismic processing, CT reconstruction, quantum chemistry, ray tracing, logistics optimization, data processing, and deep learning. The diversity and combination of applications, algorithms, and computing infrastructure are daunting. NVIDIA is a multi-domain acceleration platform with full-stack optimization for a wide range of science and industrial applications. NVIDIA is in clouds, supercomputing and enterprise data centers, PCs, industrial edge devices, robots, and cars. Our dedication to architecture compatibility has created an installed base of hundreds of millions of GPUs for researchers and developers. And NVIDIA's rich ecosystem connects computer makers and cloud service providers to nearly every domain of science and industry. The results of accelerated computing are spectacular. Accelerated workloads can see an order of magnitude reduction in system cost and energy consumption. And with the speed-ups and savings, applications from molecular dynamics to climate simulation to deep learning have scaled up 100,000 to 1 million times in the last decade. We have dedicated the full force of our company to advance computing in this new era. Today, we will update you on our latest work. Ian Buck will announce next-generation data center platforms. Tim Costa will update you on our acceleration libraries and quantum computing work. Gitika Gupta will announce new platforms for remote sensing and edge computing platforms. And Dion Harris will highlight our work in applying AI to physics, called Modulus Physics ML, and AI to physical systems, or Omniverse Digital Twins. I want to take this opportunity to congratulate Jack Dongara for receiving the Turing Award. Jack's seminal work in numerical libraries, MPI for scale-out distributed computing, and standard benchmarking to objectively measure the performance of a computer will continue to be the foundation of high-performance computing for years to come. I am very much looking forward to his Turing Award lecture. Have a great Supercomputing 2022.
Thanks, Jensen. One of the most exciting things about coming to supercomputing each year is the amazing work that's being done by the HPC community. Scientific computing is a critical tool in solving some of the greatest challenges facing our world today. Over the last year, there have been some amazing breakthroughs powered by HPC. A combined team from Stanford, Oxford Nanopore, NVIDIA, UCSC, and Google published a method where the entire genome was sequenced in just 7 hours. Currently, there are over 7,000 rare genetic disorders, and this new workflow offers hope for patients with undiagnosed or rare conditions. The University of Pennsylvania researchers have used convolutional neural networks to catalog and classify the shapes of over 27 million galaxies. They used data from the Sloan Digital Sky Survey and the Dark Energy Survey to create a model that was 97% accurate in detecting even the faintest galaxies, resulting in the largest catalog of galaxies and their shapes to date. Early detection of COVID-19 variants is paramount for the proper management of the ongoing pandemic. A team led by Kareem Bagir used a large language model with diffusion DNNs to generate a theoretical COVID-19 genome variant. They then simulated it using OpenMM and predicted the threat level using AlphaFold. Their results showed that this variant had the potential to escape immunity. This early warning system could evaluate new variants in minutes and provide critical information to help contain the spread of COVID-19. All of these amazing breakthroughs were powered by a diverse mix of systems across multiple sites, extending to the edge, connected to the cloud, and even remote sensors. We see 5 major workloads that are powering breakthroughs in HPC. At the center is simulation and the foundation of HPC, and will continue to be the bedrock of science. In addition, HPC plus AI can improve our scientific productivity by several orders of magnitude. Over the last 5 years, the number of research papers published in AI-accelerated simulation has increased by 50 times. Supercomputers are being brought closer to edge experiments, turning data collection instruments into real-time interactive research accelerators. Digital twins use simulation, AI surrogate models, and observed data to create real-time digital twins that are revolutionizing industrial and scientific HPC. And finally, quantum computing. There's a ton of research being conducted at supercomputing centers today to emulate the quantum accelerators of tomorrow. The modern supercomputer will leverage all of these technologies to solve the grand challenges of the 21st century. Accelerated computing is a full-stack problem that requires coordinated innovation at all layers of the stack. It starts with amazing hardware. Our CPU, GPU, and DPUs are integrated into hardware platforms from the edge to on-premise and to the cloud. NVIDIA Mellanox networking is the connective tissue of the accelerated data center, making the data center the new unit of compute. With SDKs, frameworks, and platforms, we aim to provide researchers the technology to build the software the world needs for the next discovery. These include Holoscan, our edge computing and AI platform that captures and analyzes streaming data from medical devices and scientific instruments. Modulus, a framework to help build AI models which learn from simulation data and physics equations. The NVIDIA HPC SDK simplifies the application development process by providing GPU-optimized acceleration libraries in ISO standard languages. NVIDIA's quantum computing technologies, cuQuantum and CODA, are helping bring quantum computing and quantum applications closer to reality. and Omniverse, which provides an open, collaborative environment to co-locate multiple heterogeneous types of data and visualize it all. As an accelerated data center platform company, we rely on our partners to build integrated solutions that power the workloads of the modern data center. The NVIDIA H100 GPUs are in full production, and our OEM partners are unveiling dozens of new HGX and OVX systems at Supercomputing this year. Be sure to stop by their booths to see the incredible work that we're doing together. The foundation of the NVIDIA stack is the processors themselves, and we couldn't be more excited about Hopper and the NVIDIA H100. Earlier this year, NVIDIA announced the H100 GPU. Built with a custom TSMC 4nm process, it features 5 groundbreaking inventions. A faster, more powerful tensor core, 6 times faster than its predecessor in Ampere. It's built to accelerate transformer networks, the most important deep learning model today. The second generation MIG, or multi-instance GPU, partitions the GPU into smaller compute units that can divide each H100 into 7 separate instances. This greatly boosts the number of GPU clients available to data center users. Confidential computing allows customers to keep data secure while being processed and maintain privacy and integrity from end to end on shared computing resources. Our 4th generation NVLink allows GPUs to communicate faster than ever before at 900 gigabytes a second of bandwidth between server nodes and scaling to up to 256 GPUs to solve these massive workloads in the AI factories of the future. The DPX instructions are dedicated cores that speed up recursive optimization problems like gene sequencing, protein folding, route optimizations, up to 40 times faster. The Golden Suite is a tool we use inside NVIDIA to measure progress across HPC, AI, and data science workloads. It's a combination of common applications like Amber, GROMACS, AMD, Quantum Espresso, Icon, Chroma, and VASP, but it also includes common AI training benchmarks like BERT Large and Resonant 50, and random forest data analysis. You can see the performance of CPU-based servers starting with a dual Broadwell system common in 2016. Over the past 6 years, CPU-only servers have only improved less than about 4x, while a P100-equipped server was already 8x faster than that Broadwell baseline. Today, we're very pleased to show how the flagship of our product line, the NVIDIA H100, achieves nearly 250 times the performance since that original system in 2016. Every day, more apps take advantage of GPU acceleration, but many hundreds of legacy applications have yet to adopt. In addition, we're entering an era where performance and efficiency must grow together. The cost of energy is more uncertain than ever. We are very excited about what our first data center CPU will enable. The Grace Superchip CPU pairs the highest performance ARM Neoverse V2 CPU core with 1 terabyte a second of memory bandwidth, and it's designed for the compute-intensive and memory-bound applications common in HPC. While Grace's performance excels, its focus is on energy efficiency and can provide up to 2.4x better performance per watt than today's CPUs. Even applications that have adopted accelerated computing have large portions which remain CPU limited, either because the cost of communication to the GPU is too high, or refactoring the vast lines of code still running on the CPU just hasn't been taken on. The Grace Hopper Superchip offers a first-of-its-kind NVLink chip-to-chip interconnect so that both the CPU and GPU have coherent access to a combined 600 gigabytes of memory. This capability bridges the gap for legacy CPU applications and makes accelerating HPC in ISO standard languages truly possible. Compared to the A100 solutions, Grace Hopper will deliver 2 to 5 times more HPC performance. Just like the Grace CPU, the Grace Hopper is very energy efficient. Depending on the needs of the workload, Grace Hopper can dynamically share between the CPU and the GPU to optimize application performance, making it an excellent choice for energy-efficient HPC centers. Assuming a 1 megawatt data center with 20% of the power allocated for CPU and 80% towards the accelerated portion using Grace and Grace Hopper, data centers can get 1.8x more work done for the same power budget compared to a traditional x86 deployment. Grace and Grace Hopper is the path forward to maximize performance and save on energy costs. In the future, every company will have AI factories. Supercomputers need to become cloud native. The NVIDIA Cloud Native Supercomputing Platform brings several technologies to provide performance, storage, and security. 1. Accelerated performance with programmable in-network computing. 2. Security and isolation, including job isolation and performance isolation. 3. Computational storage functions, including compression and file system management. And finally, 4, enhanced telemetry for smart scheduling to improve utilization of the supercomputing resources. The combination of NVIDIA's Quantum 2 400 gigabit a second InfiniBand switch and BlueField 3 DPU brings amazing capabilities of in-network computing. The NVIDIA Quantum 2 switch includes integrated hardware engines for data reduction operations, covering both small and large messages, all at 400 gigabits a second speed. BlueField 3 includes hardware engines for MPI tag matching and all-to-all communications, and of course, the ARM cores and the data path accelerator. This combination enables MPI and Nickel from the host to the network and the new DPU computing platform to increase the performance of AI in scientific simulations. As a result, we're accelerating a variety of applications by 20% or more. Microsoft ventured very early into machine learning and artificial intelligence with NVIDIA, but also has been a longtime pioneer in traditional HPC and leveraged the performance and flexibility of InfiniBand across their HPC instances. At supercomputing, Microsoft is announcing 2 new instances with the NVIDIA Quantum 2 400 gigabit a second InfiniBand networking that will turbocharge HPC workloads from CFD to FEA to molecular dynamics and weather simulation. We have already entered the era of exascale AI. In the last year, 5 new exascale AI systems based on the H100 GPUs, Grace Hopper, and Grace CPU superchips have been announced. In 2021, we announced ALPS at CSCS. And earlier this year at ISC, we highlighted Venado at LANL. The most recently announced AI supercomputers are the Mare Nostrum 5 at the Barcelona Supercomputing Center, powered by H100 GPUs, and the Shaheen 3 at the KAUST Supercomputing Center, powered by Grace Hopper superchips. We look forward to seeing how researchers take advantage of these new exascale AI systems. Next up, we have Tim Costa to share more about our accelerated libraries and the work we're doing in quantum computing.
Thanks, Ian. Today's grand challenges require simulation to occur at unprecedented scales. Simultaneously, domain scientists are focused on reducing time to science, rather than on increasingly complex computer science. Enabling developers to address this scale and technology with velocity requires a complete bottom-to-top ecosystem of software libraries, tools, frameworks, and applications with innovative features for data center scale accelerated computing. Enabling developers to focus on science starts with an investment in accelerated libraries. From linear algebra to signal processing, quantum simulation, communication, data analytics, AI, and much more, NVIDIA libraries provide a foundation upon which scientists can build applications that get the best performance from the accelerated data center while transcending hardware generations, all with drop-in ease of use. And the scope of NVIDIA libraries continues to grow, with new libraries that enable novel compute applications and groundbreaking features like multi-node, multi-GPU support. Over the past 20 years, NVIDIA's investment in enabling scientists has transformed the field of programming languages. The launch of CUDA in 2007 ushered in a revolution in the accessibility of accelerated computing. And in 2020, we announced another breakthrough with the support of standard languages running on GPUs natively with the NVIDIA HPC SDK. C++, Fortran, and Python developers can now write parallel-first code directly in their language of choice and benefit automatically from GPU acceleration. But the true measure of these software investments is in application impact. Magnum IO's Nickel optimizes collective communication patterns for multi-node, multi-GPU. VASP is one of the most widely used HPC applications in the world. We've worked with the VASP developers to integrate Nickel into the application, resulting in never-before-seen scalability. FFTs are an essential component in many scientific domains. The cuFFT library now supports multi-node, multi-GPU execution, enabling large FFTs to scale to full data center scale sizes. When integrated into GROMACS, this results in a 5x performance improvement over the existing code, as well as the ability to scale out to significantly larger problems than before. The roadmap for STUDPAR, or Standard Language Parallelism, is rich. The C++ committee is now working on adopting a new model for asynchrony called senders, which gives C++ programmers a way to express asynchrony and concurrency. This feature is expected in C++ 26, but we believe it is too important to wait, and I've created an implementation of this proposal that's available in our HPC SDK. With our senders implementation, the Palabos application for lattice Boltzmann simulation has been ported to STUDPAR. Using senders, we were able to strong scale Palabos to 512 GPUs with near perfect scaling. And remember, this is pure standard C++. No additional programming model for the GPU, for the node, or for multi-node communication. This is just the start of what's possible for developers adopting standard parallel languages in their applications. Quantum computing is a fundamentally new model of computing with many unique challenges and opportunities to impact a broad range of applications. The progress made by the community over the past decade has been impressive, from 1 to 2 qubit devices at institutes of higher education a decade ago, to systems with tens to hundreds of qubits available for general users in public clouds today. This is remarkable progress. However, to get to the point of useful quantum computing, there remains tremendous work to do. On the hardware side, quantum processor builders need to continue improving qubit scale and fidelity. It's generally understood that quantum computers will be ready to act as accelerators for some important applications when they reach a point of fault-tolerant quantum computing, with thousands to millions of qubits, error-corrected to hundreds or thousands of logical fault-tolerant qubits. Just as important is the work to be done in software, applications, and algorithms. With improved classical quantum integration and innovation in algorithms and applications, the scale and fidelity required for useful quantum computing can be reduced, accelerating the path towards useful quantum computing. To meet that challenge and prepare for a quantum-accelerated future, governments, institutes for higher education and research, as well as industry, are investing heavily across the board in hardware, software, and algorithm development. GPU supercomputing is essential for quantum computing in 2 areas. The first is quantum circuit simulation. With quantum circuit simulation on the NVIDIA platform, researchers can develop algorithms at the scale of valuable quantum computing long before the hardware is ready. On the NVIDIA platform, we're already simulating quantum algorithms with tens of thousands of perfect qubits, representing the future state of fault-tolerant quantum computing. The second area where GPU supercomputing is essential is hybrid quantum classical computing. As we move past basic algorithm R&D and work on building full quantum applications with tight classical quantum integration, a platform for hybrid quantum classical computing with emulated quantum resources is an essential research platform. Long-term, all useful applications of quantum computing will be hybrid, with quantum computers acting as an accelerator for key kernels alongside GPU supercomputing. In 2021, we introduced cuQuantum, an SDK for accelerating quantum circuit simulation. cuQuantum is built to accelerate all circuit simulation frameworks and is integrated into Cirq, Qiskit, PennyLane, Orchestra, and more. With cuQuantum, researchers can simulate ideal or noisy qubits with a scale and performance not possible on today's quantum hardware or with unaccelerated simulators. cuQuantum has been adopted by a broad range of groups spanning the entire quantum ecosystem, including supercomputing centers, academic groups, quantum startups, and some of the largest companies in the world. BMW is leveraging cuQuantum to optimize pathfinding and routing for robots. Large consultancies like Deloitte and SoftServe are developing applications in quantum machine learning for both materials and drug discovery to address their customers' most pressing problems. Fujifilm is leveraging cuQuantum to explore tensor network methods for material science simulation with thousands of qubits. The cuQuantum appliance is a container consisting of leading community frameworks accelerated by cuQuantum and optimized for the NVIDIA platform. Coming in Q4 of this year, the cuQuantum appliance will provide native multi-node, multi-GPU quantum simulation. This means scientists can leverage an entire accelerated supercomputer as a single quantum resource through a software container with the same familiar interfaces they are using for their quantum work today. Recently, researchers leveraged the cuQuantum appliance to participate in the ABCI Grand Challenge. A variety of problems, including quantum volume, quantum phase estimation, and the quantum approximate optimization algorithm, were run across 64 nodes on up to 512 GPUs. The performance achieved was up to 80 times better than alternative multi-node quantum circuit simulation solutions, enabling problems at scales that would otherwise be time prohibitive. We're really excited about the results our partners are seeing leveraging cuQuantum to accelerate their work, and I'd like to point out a few recent highlights. We recently partnered with Xanadu to integrate cuQuantum into PennyLane, the leading framework for quantum machine learning, and with AWS to make that available to customers through their Bracket service. Combining these tools, AWS saw a speed up of over 900 times on simulating quantum machine learning workloads, along with a 3.5 times reduction in cost for their users. Xanadu is also leveraging cuQuantum for research into novel quantum algorithms at supercomputing scale. In general, the ability to simulate quantum circuits is limited by system memory, with the world's largest supercomputers limited to qubit scales in the mid to high 40s. Using a novel circuit cutting technique, they were able to accurately simulate the quantum approximate optimization algorithm with up to 129 qubits, running on Perlmutter through NERSC's Quantum Information Science Initiative. And Johnson & Johnson, who recently spoke about this result at our GTC conference, has seen a 100 times speedup from cuQuantum for their work applying a variational quantum eigensolver to the 7-mer protein folding problem in a collaboration with StrangeWorks. A critical consideration as we look towards the quantum-accelerated applications is that they will not run exclusively on a quantum resource, but will be hybrid quantum and classical in nature. In order to transition from algorithm development by quantum physicists to application development by domain scientists, we need a development platform built for hybrid quantum classical computing that delivers high performance, interoperates with today's applications and programming paradigms, and is familiar and approachable to domain scientists. To address this challenge, we recently announced NVIDIA Quantum Optimized Device Architecture, or CODA. CODA is the platform for hybrid quantum classical computing built to address the challenges facing application developers and domain scientists looking to incorporate quantum acceleration into their applications. CODA is open and QPU agnostic. We're partnering with quantum hardware companies across a broad range of qubit modalities to ensure it provides a unified platform that enables all hybrid quantum classical systems. CODA integrates with today's high-performance applications and is interoperable with leading parallel programming techniques and software. It allows a domain scientist to quickly and easily move between running all or parts of their applications on CPUs and GPUs, simulated quantum processors, and physical quantum processors. And now I am really excited to show our first proof point running CODA with both an emulated quantum resource leveraging cuQuantum and on a physical QPU, Quantinuum's H12 processor. In this experiment, we're running the variational quantum eigensolver. VQE is a hybrid algorithm for computing the ground state of a Hamiltonian and is key to both quantum chemistry and condensed matter physics. The plot on the left is simulated with CODA compiled to a cuQuantum backend running on an A100 GPU, representing what you expect from perfect qubits. The plot on the right is the exact same CODA code, now compiled to execute the quantum kernels on the Quantinuum processor, simply by altering a compiler flag. This is a simple example, but demonstrates how easy it is to use both quantum and classical computing resources with CODA. And this is just the start. We will continue to work to enable all quantum processors to be accessible through CODA, ensuring that researchers can leverage the best resources for classical computing, simulated quantum computing, and physical quantum computing. And now Gitika will tell us about new platforms for remote sensing and edge computing.
Thanks, Tim. Scientists use instruments like electron microscopes, telescopes, X-ray light sources, and particle accelerators to further their knowledge and understanding for all kinds of matter. For example, researchers at Argonne National Lab are experimenting with enzymes to tackle plastic waste. Using AI models trained on 19,000 protein structures, they shortlisted specimens to examine and confirm their hypothesis using an X-ray beamline at the advanced photon source. These instruments that are playing detective at a nanoscale level are often as big as a football field. They're spread out all over the world, from Australia to UK to South Africa. Millions and billions of dollars of investment is taking place right now to upgrade them. After the upgrade, these instruments and sensors will produce up to 500 times brighter rays, generating crisp, clear, and high-resolution images. This huge jump in the brightness translates to 1,000 times more data, easily running into petabytes and exabytes. This poses a data analysis and data migration problem. The streaming data software pipeline should be multimodal, easy to use, scalable, flexible, and include AI and ML techniques to filter the most relevant bits of information in seconds instead of days. Let's first look at how these experiment sites or labs are laid out. Be it Oak Ridge National Lab or a university like Purdue, the campus typically may have a center for biosciences, material science, nanotech, robotics, or advanced manufacturing with a small number of workstations and servers connected to the main computing center. The site may also be receiving data from other sister sites and remote sensors out in the field. For such a multidisciplinary campus, investments in compute, storage, and connectivity are key to support open science projects. InfiniBand that can run end-to-end, data center to data center, enables researchers spread within or across sites to collaborate. Data coming from an experiment at one end of the campus can feed into another instrument sitting in a separate building in minutes instead of days or months. Today, we are announcing multiple products where NVIDIA is investing to enable scientific discovery that spans from the edge to the data center. NVIDIA Holoscan is an SDK that can be used by data scientists and domain experts to build GPU-accelerated pipelines for sensors that are streaming data. The developers can use C++ or Python APIs to build modular blocks that are flexible and reusable. For added performance, they can also include JAX, machine learning, or AI. Holoscan sits on top of GXF that manages the memory allocation to ensure zero-copy data exchanges, so developers can focus on the workflow logic and not worry about file and memory I/O. The new features in Holoscan will be available to the HPC developers in mid-December 2022. The second piece of the solution is NVIDIA MetroX3, or long-haul InfiniBand. InfiniBand is synonymous with server racks standing side by side, but MetroX3 extends the reach of InfiniBand network to up to 25 miles or 40 kilometers. Now, taking advantage of native RDMA, users can easily migrate data and compute jobs from one InfiniBand-based mini cluster to the main data center or combine geographically dispersed compute clusters for higher overall performance and scalability. MetroX3 systems are managed by the NVIDIA Unified Fabric Manager, or UFM. UFM enables data center operators to efficiently provision, monitor, and operate all the InfiniBand data center networks. MetroX3 systems are going to be available end of November 2022. The third piece is Bluefield 3 DPU using intelligent storage offloads for data migration. At Supercomputing, ZR is demonstrating their data migration solution with Bluefield 3 for InfiniBand connected data centers and remote HPC sites, where an x86-based solution needs 13 U of rack space. With Bluefield 3, it can be accomplished with just 4 U of rack space. UT Southwestern is one of the customers evaluating MetroX3 to connect their healthcare researchers who are using a dispersed compute infrastructure. As part of the initial research project, they are connecting the UT Southwestern West Campus with a cluster that is about 10 miles away. MetroX3 customers can also take advantage of NVIDIA's full-stack architecture. This includes native RDMA, in-network computing, GPU Direct, and ease of management with UFM to operate the compute nodes that are miles apart as one large supercomputer. Scientific discovery in this decade will come from an end-to-end converged workflows comprising the data coming from various experiments at the edge, feeding into simulation, and training AI models running in the cloud or data center. For HPC at the edge, Holoscan SDK can be used to develop data streaming pipelines to convert raw data into actionable insights in seconds instead of days or weeks. By analyzing data as it's being generated, the researcher can avoid errors, retries, and false starts. Added benefit is that the researcher can steer and control the experiment as the data is being collected, make decisions and discoveries on the spot. Filtered and compressed data can be sent over MetroX to the main data center on campus or into the cloud, not only for archiving, but for a lot of interconnected applications. Observational data can be used to enhance simulations, train or refine AI surrogate models, or can be fed into a digital twin. Offline simulations, AI surrogates, and what-if scenarios from digital twins can recommend parameters for the next experiment. To enable the converged workflow for scientific discovery, NVIDIA is investing in Holoscan, GXF, and UCF. UCF stands for Unified Compute Framework that enables developers to combine optimized and accelerated sensor processing pipelines as microservices from the cloud. Supporting the new era of scientific discovery will need workflow management systems that can orchestrate all the moving parts and are not bottlenecked by data migration, disk copies, and file transfers. HPC community and those working on adapting the workflow management systems can pick up Holoscan and UCF to maximize the utilization of all the instruments run simulations, do AI training, and even build interactive digital twins. To elaborate more on AI and digital twins, Dion Harris will walk you through Modulus and Omniverse for HPC.
Thanks, Geethika. AI is quickly becoming the fourth pillar of scientific discovery. For centuries, science has been built on the foundation of three pillars: observation, experimentation, and theory. More recently, HPC has become a critical tool in scientific research. HPC simulations are important because they allow us to study things that happen too slowly or too quickly to observe in real time. AI allows us to reshape and accelerate the scientific discovery process. By training a model on observed or simulated data, we can create a physically informed AI model to predict new scientific outcomes. These predictions are then verified by experimental observations, and the model continues to evolve over time. The power of AI is that it can automate the process of doing simulation by analyzing data. This means that we can take on problems that were too big or too complex for traditional scientific methods. We can now use AI to help us find new cures for diseases, design new materials, or find new energy sources. AI is not just a tool for science, it's a new way of doing science. NVIDIA Modulus is an AI and training inference platform that enables developers to create physics-ML models to augment and accelerate traditional simulations with high fidelity and in near real time. Today, we are announcing Modulus is available via NVIDIA Launchpad and several major CSPs. Modulus accelerates a wide range of scientific applications. Climate and weather simulations are critically important to develop policies to help fight climate change. NVIDIA collaborated with Lawrence Berkeley National Labs and researchers from the University of Michigan, Rice, Purdue, and Caltech to build an AI model called ForecastNet that performs extreme weather predictions 45,000 times faster and 12,000 times more energy efficient than conventional numerical simulations. To fight climate change, consumer electronic companies can design more energy-efficient products to reduce their carbon footprint. NVIDIA research used Modulus to optimize the design of our workstation GPU heatsinks, resulting in 35% higher power densities on the GPU when compared to conventional vapor chamber and heat pipe combinations. Siemens Gamesa is using NVIDIA Omniverse and Modulus platforms to improve wind farm simulations, enabling them to create more accurate models of complex interactions between turbines using high-fidelity, high-resolution simulations that are based on low-resolution inputs. This will help to optimize the performance of its wind farms and reduce the maintenance costs. Finally, industrial plants and facilities are complex to plan, build, and operate, whether factories, warehouses, or even data centers. For the 7 million worldwide data centers, achieving optimal performance and energy efficiency is of paramount importance. Let's take a look.
NVIDIA Omniverse can be used to build digital twins of high-performance data centers to help optimize every step of planning, building, and operating complex supercomputing facilities. In constructing NVIDIA's latest AI supercomputer, engineering CAD datasets from tools like SketchUp, PTC Creo, and Autodesk Revit are aggregated so designers and engineers view and iterate on the full-fidelity USD-based model together. With Patch Manager connected to Omniverse, the complex topology of port-to-port connections, rack and node layout, and cabling can be integrated directly into the live model. Next, CFD engineers use Cadence Six Sigma DCX to simulate thermal designs. Engineers can leverage AI surrogates trained with NVIDIA Modulus for real-time what-if analysis. And with NVIDIA Air, a network simulation platform connected to Omniverse, the exact network topology, including protocols, monitoring, and automation, can be simulated and pre-validated. Once construction is complete, the physical data center can be connected to the digital twin via IoT sensors, enabling real-time monitoring of operations. With the perfectly synchronized digital twin, the engineers can not only simulate common dangers, such as power peaking or cooling system failures, but also validate software and component upgrades for CI/CD before deploying to the physical data center. With digital twins and Omniverse, data center designers, builders, and operators can streamline facility design, accelerate time to build and deployment, and optimize ongoing operations and efficiency.
Digital twins are evolving. NASA used physical twinning to duplicate spacecraft on the ground that matches spacecraft in orbit. On April 14, 1970, this approach was used to resolve the Apollo 13 oxygen tank explosion from 200,000 miles away. The term digital twin was coined by John Vickers of NASA in 2010 when they created digital simulations of spacecraft for testing. Batch simulation digital twins are built on large amounts of data generated from complex simulations that can take days or even months to complete. The advancement of IoT, cloud computing, and AI has created a new class of interactive digital twins. Siemens Energy built an interactive digital twin of its heat recovery steam generator plant to develop new workflows to reduce frequency of planned shutdowns while maintaining safety. By simulating and visualizing the flow conditions in the pipes, Siemens Energy can understand and predict the aggregated effects of corrosion in real time. Virtual and physical steering digital twins are on the horizon. Bill Tang at the Princeton Plasma Physics Laboratory and researchers from Argonne National Laboratory have developed an AI model called SG22 to simulate the plasma physics of a fusion reactor. When paired with NVIDIA Modulus, SG22 will be included as a part of a real-time control system to optimize the operation of fusion reactor experiments, operated in NVIDIA Omniverse. Here, a researcher generates simulation data to measure the state of fusion plasma, visualizing it in ParaView. Two more researchers are using particle code simulations and surrogate models to further simulate and explore the state of the plasma. However, scientific research and simulations don't exist in a vacuum. The infrastructure design and 3D CAD elements are critical to understanding how the system will behave in full production. Today, each of these four workflows exists separately, with no way to see the combined interactive model. But now with NVIDIA Omniverse, researchers can connect ParaView and 3D CAD datasets to see their aggregated model in real time. And when ingested into Omniverse, their visualization workloads are accelerated by core Omniverse technologies: RTX ray tracing, Index, NeuroVDB, PhysX, and Modulus, creating a real-time end-to-end workflow. Omniverse is an open development platform, bridging the physical and virtual worlds, so teams building these virtual simulations can connect them to physical worlds to build a virtual physical steering digital twin. The scientific community is in the early stages of adopting AI and digital twin technologies. NVIDIA is committed to partnering with researchers to advance science and make these technologies more accessible. And today, we are announcing Omniverse for HPC. Omniverse now supports batch rendering and synthetic 3D data generation workloads on NVIDIA A100 and H100 systems. With Omniverse Nucleus also supported on A100 and H100 systems, the scientific community can now take full advantage of more streamlined collaborative workflows across multiple applications, multiple teams, and even multiple continents. To achieve full fidelity interactive digital twin simulations, customers can adopt NVIDIA OVX powered by L40 GPUs, a computing system purpose-built for developing and operating persistent virtual worlds. If you have an NVIDIA A100 system, you can get started with Omniverse today. All over the world, extreme weather events are becoming disturbingly common. The last decade has seen some of the most damaging floods, storms, and wildfires in recorded history. About a year ago, we announced our Earth 2 initiative to help the scientific community tackle climate change, one of the greatest challenges of our time. A challenge of this magnitude will require a long-term commitment and collaboration across government, researchers, and industry. Today, we are announcing that Lockheed Martin and NVIDIA have been selected by the National Oceanic and Atmospheric Administration to deliver the foundational technologies for the Earth Observation Digital Twin Project. When completed, this project will lay the groundwork for building the Earth Observation Digital Twin of NOAA's next-generation ground enterprise system. We are at an inflection point. The ability to create digital twins of physical systems and then use AI to control and optimize them in real time is revolutionizing many industries and scientific domains. We are just scratching the surface of what's possible, and I'm incredibly excited to see what the future holds. Ian, back to you to wrap things up.
NVIDIA's multi-domain acceleration platform is at the forefront of the accelerated computing era and the engine of the modern supercomputer. We are excited to see how H100, Grace Hopper, and Grace CPU superchips deliver unmatched performance and, most importantly, energy efficiency. And our cloud-native supercomputing platform, delivers scalable, secure, high-performance infrastructure. To develop scientific computing applications, our HPC and quantum computing SDKs allow users to scale performance and accelerate both traditional and quantum computing simulations. Supercomputing is reaching to the edge with the help of Holoscan, while Modulus and Omniverse are accelerating today's HPC workflows and introducing a new era of fully live, interactive digital twins for scientific use cases. The future of supercomputing is exciting, and I hope to see all of you at SC22.